So the Cauchy-Riemann equations and differentiability, that's what we're going to start off with, and then we'll move right into a fundamental application. So we have differentiability, so functions of a complex variable, fz, we're talking about now. So they're defined in the entire complex plane, and you can also write them as u of x and y plus I v of x and y. But the definition of the derivative is the same as before. So we have f prime of z equals limit delta z goes to 0, f of z plus delta z minus z. And that defines a derivative, and as I pointed out, you have to be able to approach your derivative from any direction. So it's not just along the real axis, you have to approach it from anywhere. And under those circumstances, they're very restricted actually, and you get the Cauchy-Riemann equations, which are du dx equals dv dy, and du dy equals minus dv dx. So those are the Cauchy-Riemann equations. And I'm just going to use this equation, Cauchy-Riemann equations. So they follow from a complex function being differentiable. Okay. But of course the definition of derivative is exactly the same. So there are a bunch of consequences of this. I'm just going to mention one, and let's just go ahead and we've got a consequence of the Cauchy-Riemann equations which follow from differentiability, and that is, let's just do the following. If you do d squared u dx squared, that would be a second derivative. We're differentiating both sides with respect to x, so we'd have d squared v dx dy, and then d squared u dy squared, we'll do that on this side, is negative d squared v dy dx. Well, what do we see about the right side of both of those equations? You know, as long as your function's well behaved, these mixed partials are the same. Right? The order is irrelevant. And this second one is the negative of the first one. So what you get is d squared u dx squared plus d squared u dy squared equals 0. That's a two-dimensional potential equation, for example. And I should also note, you could do the same thing for v. Same for v, you end up with d squared v dx squared plus d squared v dy squared equals 0. So this is kind of an interesting result, because all we required was that our f of z be differentiable. F of z is differentiable, and its real and its imaginary part both satisfy the potential equation. So there's an entire field of study of the potential equation in electrostatics, where the field of complex variables can come into play. Same for applications of fluid mechanics. I'm just going to write here applications in electrostatics, fluid mechanics, and in general, all manner of two-dimensional physics. Okay? We're not going to go there, but it's something to be aware of because we'll run into that. Electrostatic type of problems in 2 dimensions, suddenly, you know, your authors, your texts, and teachers will be using complex variables. Okay? These techniques are there, fluid mechanics. So 2-dimensional physics in general makes great use of complex functions. And let me just give a quick, not trivial, but almost trivial example. What's an example of a differentiable function in Z? Z itself, or Z squared, right? Those are differentiable functions. So let's just do Z squared and look up the, I'm gonna erase this. Just to make sure we see what's going on here. We're not gonna pursue this because we have other goals, but you definitely want to be aware of it. Okay. Be aware of it. So the example for this, f of z equals z squared, right? That's differentiable, its derivative is 2z. No more need be said, okay? So that's differentiable if we do equals x plus I times y squared. We know that's x squared plus 2ixy minus y squared. So that's x squared minus y squared, also parentheses here, plus I times 2xy. So the function that I'm talking about, u and v, this is our u of x and y, and this is plus, this right here is our v of x and y. Okay. So now what do we have if we do this top equation, d squared u dx squared plus d squared u dy squared. We can just read it off right here. Second derivative, first derivative is 2x, second derivative is 2. Then it's going to be minus 2, and it's going to vanish. And the same thing for the second derivatives here, but of course, they're going to vanish. So this is an analytic function. These are solutions to, say, the potential equation. They would have electrostatic examples, corollaries. And, you know, it would get more complicated. You could do z cubed, z to the fourth, etc. But I just wanted to make sure you're aware of that, because you'll run into any time there are two-dimensional systems. And that can be three-dimensional systems that are uniform in the third dimension, right? That counts as a two-dimensional system. Then you will find that complex variables are being used a lot. But what we want to do is integration in the complex plane now. So differentiation is just the way we always learned it. So like I said, I'm skipping some of these applications. And in my notes I have an example from fluid mechanics and all kinds of stuff. But we're going to talk about integration next. So here we go. So this whole next chapter is called the Cauchy integral theorem. See how much of it we're trying to get through today. And the definition of the integral in the complex plane is very natural. Pull out a note or two here. In fact, I'm going to expand on what I have. But we'll call this integration first, and then we'll talk about the Cauchy. Integration in the complex plane. So we now have the idea that we have some curve in the complex plane. And we're going to take some S sub n, we're just going to define as, and we've got a function, f of z. Okay, we're in the complex plane, we've got a function f of z, we want to integrate from a to b. So you'd say, we want some kind of f of z dz of a to b in the complex plane. What we'll see is this is perfectly formulated. If we do an f of z sub I plus 1 minus d sub I, and imagine that we have some kind of subdivision of that interval there, of that contour. What you can see here is this z sub I plus 1 minus z sub I, because of this vector nature of the complex numbers, it is literally a little directed segment. That's what that difference is. It's a directed segment. So if we have a curve defined, we can see that the integral f of z dz, we need I'm just going to write curve a to b here, is just going to be this limit of s sub n as n goes to infinity. Because what we're doing is we're going to do a subdivision of these more and more, and finer and finer. And the nature of this difference here, this dz, literally is the directed segment along the equator. I'm going to remind you guys of the Riemann sum for the real integral, which will actually be useful for this. So I'll put here recall integral f of x dx from a to b. And let's have a really concrete example here. We've got an interval a to b. We've got a function out here. And you guys remember how that integral was defined as the area under the curve? So for that definition, you would have been taking a bunch of little rectangles there, you'd make them finer and finer, and then in the limit as they get really fine, you define it as the area under the curve. So let's explore that. Just to get practice for what we're going to do over there, which is not going to be any more difficult. Okay? So here we would have had, here we could say this s sub n could have been sum I equals 1 to n. Let's see if we can do this. F of x of I delta x of I. Now this time I can define all these things. So my delta x of I is, I'm going to make it uniform all the way across there. It's going to be b minus a divided by n. Right? It's going to be that interval there divided by n, and then my x sub I could say it's A plus B minus A divided by N times I. And what I'm doing then, my delta x of I is this width, and then I'm evaluating it up there, and so forth, all the way across. And clearly the limit of this as n goes to infinity, I'm just making these finer and finer, more and more of those. So that's how we learned integration when we learned about Riemann sums. And limit n goes to infinity, s of n is what we'll call the integral f of x dx, a to b. That's a good one to keep in mind. The fundamental theorem of calculus can also be shown with this same construction. I'll erase this over here, we'll just put it back up there in a minute. So the next thing we have f prime of x dx from a to b is equal to f of b minus f of a. Okay. So that's one way to look at the fundamental theorem of calculus. Now, if we do that same construction that we did over there, we would now have a sum of f of x of I minus f of x of I minus 1, x of I minus x of I minus 1. So this would be our difference quotient. And then our delta x would be x of I minus x of I minus 1. And we would integrate these or sum these from I equals 1 to n. Okay. So that would be the left side, the integral, the sum. And we can see in the limit, as n goes to infinity, it's the same construction as there. It's just getting finer and finer. Okay. So for any one of these, we're good. But this one here, this is the difference quotient, there's the little delta x. You see they cancel identically, and you end up with f of x of I. Oh, no, actually, let's just look at it and write it down. These can't, these you can cancel against each other. And then you're always taking f of x of I minus f of x of I minus 1. So you're systematically canceling them all, and you're left with f of x of n minus f of x sub 0, which is I equals 0, right? F of a, right? So f of x of n, x of 0 equals f of b minus f of a. So it's good to see these constructions in play, because in physicists, we're going to have to invent something at some point in our lives, right? So this is this very same construction here for the fundamental theorem of calculus. And you'll notice when I replace that complex definition up there, both of those hold true for the complex numbers as well, exactly as for this. With the difference that here we literally defined our curve, so to speak, and we're just an interval on the x-axis, and the other one we're assuming some curve through the complex plane. Okay. So both of these theorems in construction hold true for the complex numbers. That's the point I'm going to stress. These are the real constructions. So both constructions S of n. Infinity, sum over f z sub I minus z sub I minus 1. However you define it, decide to number these, right? Both of these hold true, and also in the complex plane, if we've got an A and a B, this is going to be F of, I'll just call it B minus F of A. Again, this one was that picture we had where we're now going there with some kind of curve. And so you have to just be able to get a parametrization of the curve in the complex plane, but that's not that. I mean, there are plenty of simple ones. The ones we're going to do are especially simple. So yeah, we have both of those. In other words, what we know about integration in terms of just basic rules are going to hold true here in the complex plane. So the next thing is called Darboux inequality. So Darboux inequality. So this is a triangle inequality. Generalized. So what we do is this. We take this S of n we have over here, F of z sub I minus F of z sub I times z sub I minus z sub I minus 1, and we know that that's our approximation to the integral, arbitrarily good. And we're trying to find a bound for it. So just by the rules of products of complex numbers, we could bring this inequality inside the sum of z sub I times z sub I minus 1. Okay, so we've got an inequality there, and we can do it for the products of these. F of z sub I, z sub I minus z sub I minus 1. Less than or equal to the maximum on the complex plane of our function f of z, magnitude. And what would we have here? Times the sum over z sub I minus z sub I minus 1. What is this thing going to be? This is going to be the approximation to the length of the curve. And I'll go ahead and draw a sketch for that in a minute. So less than or equal to maximum value that our function takes, wherever it's defined, times here the length of the contour. So yeah, the picture that goes with this, important inequality. You can draw a little larger one. Okay, Okay, so we're here in the complex plane, we've got our point A and B, and we've got a curve that connects A and B, and that's what we were integrating along and summing along. Any of these two differences, I'll go ahead and draw them right here, you know, well, these two numbers here, say this is Z sub I, this is Z sub I plus 1. Chord across there. That's the difference in these 2 points, and as we made them closer and closer together, we were approximating the curve more and more. This is also the formula for the length of the curve. Say I were approximating this curve with these 3 Z's, right? Should have put it at B, but you get the idea, right? As I make these magnitudes, see the magnitude of this difference is precisely this length, and it's approximating the curve. So clearly this limiting case took us to the length of the curve there. That's the Darboux inequality for taking the limit as n goes to infinity. We have the inequality, we then have integral f of c dc, a to b magnitude is less than or equal to maximum value that f takes. By the way, magnitude of the maximum value, or maximum of the magnitude, times the length of the curve L. L, yeah. And in fact, I may as well do these symbols here. So we just have a curve C, and then here I'll write length of C. This is what I have in my notes, length of the curve C. Good, so now let's actually do one of these. Concrete case. And we got room right here. So the example. We're going to integrate dz over z squared. I'm going to call this c sub ab. And here's the c sub ab is this, minus r plus r. This is our point A, and this is our point B. So we're not integrating over the real axis at all. We're starting here, and we're integrating in this direction. We're actually doing a lot of these. Integrating A to B, from A to B along that semicircle there. So how do we set this one up? I'm going to make some room to the left here. They're surprisingly easy. Okay. So this curve here, this is our curve CAB, right? So A is the semicircle there. So to do this integral, integrate, let C equal e to the I theta, and now we got to pull an R out there. Let Z equal R e to the I theta. Then when theta is 0, I'm here, and when theta is pi, I'm there. And theta is the parameter for this curve that takes us clearly through the big arc in the complex plane. dz is just I r e to the I theta. You guys remember that example where we're here somewhere, and there's the theta, and then we said multiplying that number by I, this shifts it by e to the I pi over 2, right? So that DZ really is that directed arrow there, the DZ all the way around the arc there. So now we have an integral the CAD DZ over Z squared. It's going to be less than or equal to the maximum of this 1 over Z squared magnitude times the length of the curve, length of C. Let's go ahead and do this a little bit more. So we have 0 to pi I R e to the I theta. Oh, I forgot, guys. E theta. We called it that? I R e to the I theta d theta. So I R e to the I theta d theta. And the denominator is that Z squared, which is R squared e to the I times 2 theta. Magnitudes here, you have R over R squared, so we've got a 1 over R. What else do we have? Magnitudes, let me go ahead and do this in 2 steps. We've got 1 over R, we've got 0 to pi, just so you see pi, e to the I theta, e theta, e to the I times 2 theta. So we're doing magnitudes less than or equal to, now we're right there. And the magnitude of I is 1, the magnitude of e to the I theta is always 1. Same with the denominator. So those are all 1s, and we're getting 1 over R integral 0 to pi d theta. This is pi over R. And this is nice. What happens when R goes to infinity? There we go. We get 0. So this is going to be something we do a lot of in this class. And this is actually sufficient to make up for that limit we took when we did the Fourier transform of the Gaussian. Remember the Fourier transform of the Gaussian? We had some limits, out there in the complex plane. As they were going to infinity, those things were just vanishing, regardless of what their value was. Pushing them out to infinity makes them vanish. So we're going to do a lot of this here. So this is a good example. We have the concrete application here, or the concrete evaluation of this integral here. And the maximum value of the 1 over Z squared was, of course, the R squared. So we see here. Good. Let me see. So these are really important integrals. And what's going to happen again and again is we're going to be interested in this integral. We're going to use theorems that evaluates the thing in the entire complex plane, and we're going to throw away this one because it goes to 0. So that's going to be the key here. But first we have to learn Cauchy's integral theorem. So that's the next one. This one I want to do pretty thoroughly because everything is based on it. So many things that follow are based on it. closed contour in the complex plane let f of c be analytic in that contour, within it and on it. So f of c be analytic in and on C. So the contour C and the complex plane C with that thing right there, two different things. Well, if you remember what analytic was, analytic simply means first derivative exists. Okay? First derivative. But in the what we specified about it, so f prime of C exists. Okay. That's analytic. Then the integral f of C dz around this closed contour is equal to 0. That's the whole theorem. And we're going to prove it. We're going to prove it just using this property here that was analytic. Okay? So here's the proof. Sure, we'll put enough of this here. So we've got we have an oriented contour, which means that positive direction here. We've got an oriented contour. So C is the outside oriented contour. Okay. And what we're going to do is the following. We're going to build this grid here. You guys may have seen something similar with Stokes' theorem. In each one of these boxes, we can integrate around in an oriented contour. And the thing about these boxes is we're just gonna about these boxes, so these are two colors. If we have two adjacent boxes, they share a contour. So the adjacent contours cancel, right? If you were to do the integral around this box and this second box, the ones that are adjacent would cancel. And if you do that around all of these boxes, I'll do a couple more. Here. If you're to do it around this one, these two adjacent contours. And same here, we're just going to call this box, this one with the triangular shape here. What that means is the integral around the outside contour is equal to the integral around this, or the sum of integrals around all these boxes. So we have integral f of z dz, that's the outside contour, equals the sum of these integrals, integral c sub j, and there's my symbol for that box, f of z dz, over all the j. And the reason is because these adjacent sides cancel. I don't know because adjacent sides cancel. Sides cancel. Good. So next we have to do a construction and then an estimation. Adjacent sides cancel. And as in that picture there, I have a second picture here. So next we're going to define a function delta of z and z sub j equals f of z minus f of z sub j, z minus z sub j minus df dz evaluated at z sub j. So what is this? So here I've just taken, some z sub j. It's in one of those boxes. So delta of z and z sub j, it's always in the jth box, and it's defined this way. And if you look closely at this, what is this definition? It's the difference quotient anywhere in this box minus the derivative at z sub j itself. And so we're making use of the fact that f is analytic, right? It's analytic, so that derivative actually exists there. So we do that, and then we just solve this, or we've defined this, right? You can see difference quotient minus derivative. And so each of these deltas is in that jth box there. And we're going to solve it for okay, yeah. I'm going to note the magnitude of this delta z sub j can be made arbitrarily small. Just by making the box smaller and smaller. And so, you see what we would be doing here? In other words, we're just saying we can make this arbitrarily small because if we make the box small enough, then the derivative and the difference quotient can be made arbitrarily close together. So, i.e., given epsilon greater than 0, and choose box so that delta of z and z sub j is less than epsilon. Doesn't matter how small. You can choose the epsilon as small as you want. You can just make the boxes smaller, small enough so that this thing is that small, because this is just the difference between the difference quotient and the derivative. So now we're going to go ahead and estimate this thing and solve for f of z. So we'll just multiply this out and solve for f of z. I'm going to erase this. And in fact, I will say now, let's name this star like we name everything star. Now solve star. Solve for f of z and integrate. So what do we get here? F of z, we've got f z sub j, z, just the way we perform this, f of z sub j plus f prime of z sub j, z minus z sub j. Remember we started with the that when we were talking about the derivative earlier on. And then we just have this delta times z minus z sub j as well. Plus delta z sub j, z minus z sub j. So we've solved for f of z. And now we're going to integrate. So integrate integral of f of z dz around c. We know we have that. I'm going to write this down. Equals ... We have integral around the box sub this all that's left over? Right, I'm gonna have some of these box integrals, so that's fine. I'm gonna plug this into that integral here. And the reason we're only going to have this one left over is because f of z sub j is a constant. We're integrating the box around a constant, okay? That's closed integral 0. This is a constant times z sub j, expanding this one out, a constant integrating around the closed box, the closed circle, also is 0. This z here, has an antiderivative closed, just what I proved with the fundamental theorem, right? So that's why all of these go away when I integrate around the box, and I'm just left with this one. Make a note of that. I just said it. Constants, integral around closed curve equals 0. And same with the linear in z, integral around closed curve, got an antiderivative equals 0. So that's why those are 0. So this is the last one we don't know about. And what we're going to do is estimate this one. So this was an integral around jth box, and we know we have to sum all of them up. So those integrals will vanish. And getting rid of this now, I'll leave the picture in here. Picture's good to have. So here we go. Now, this is our outside contour. We know it's equal to magnitude of the sum of all of those integrals, f of z dz. And now from that argument, we know that it's equal to the sum of all of these integrals around the jth box of this delta of z at zj, z minus zj, dz. And less than or equal to sum over j magnitude delta z zj z minus zj. So now we're going to estimate this. Let S of j equal side of a box. So S of j is the side of one of these boxes. Then delta z sub j z minus zj magnitude is going to be less than or equal to epsilon square root of 2 s sub j. Because now I'm invoking the fact that I can make these boxes as small as I need. Right? Any arbitrary small number epsilon. And then I've got square root of 2sj as the diagonal of a box. Okay. this integral here is now less than or equal to sum over j epsilon root 2 s sub j and 4 s sub j, because this is by Darboux. This is the length around the perimeter, Darboux equality, so this is Darboux. And this is what I just made use of here. Arbitrarily small box, root 2 diagonal. And what do we end up with here? We've got less than or equal to root 2 epsilon. We'll pull the 4 out here as well. And then we'll have sum of all sj squareds. And this is where we have everything, okay? Because 4 and root 2, who cares, right? What's the sum of sj squared? That's the area here, okay? So sum of sj squared area. So this integral thing, this thing we've gotten here is epsilon times 4 root 2 times the area enclosed. And this is just a finite number. And what about the epsilon? Arbitrarily small. So that's how you declare something to be 0. And that's how you declare it to be 0. This is a finite number, this is arbitrarily small, therefore that's the proof that that integral is 0. So this is actually a good one, because I didn't make it up, but I wish I had. Because there are a lot of proofs of Cauchy's theorem, and some of them are very involved and long. But this one's pretty thorough and definitely gets all the ideas across. And what did it use? It used Darboux's theorem, which is just a basic fact of these things. And it used the differentiability, right? The whole construction of this came about because the function is differentiable. So anyway, if you like mathematical analysis, this is one you can ponder. But we're going to draw a bunch of conclusions off of it. And I just wanted to be thorough about it because we're going to make so much use of it, and you could play around with it if you want. Good. Good. So I should write that down. Epsilon arbitrarily small. And that's how we conclude that that won't be 0. Because this is always. Okay, let's get an application of this to round up the here. So one way we apply this often is in multiply connected domains. So I'll say something general about that, and then we'll do some examples. So multiply connected domains. places where your function's not defined. And what you do is draw a circle around these, 3 of them, and then you connect this whole thing in one contour. So say I would be going around the outside of this, I'd come in here and go around these here clockwise, and then I'd leave again the same way I came in. And I'll do that 3 times. I can do that. So you always go around clockwise here, leave the way you came in, and because of that, you can apply Cauchy's theorem to this new total contour. Okay. So integral f of z dz c, I'll call this C1, C2, C3, C0. C0 plus C1 plus C2 plus C3. That's the contour you're going around. And now you still have, for multiply connected domains, if you have this complicated contour, you still have Cauchy's theorem. Because you've gone around these 3 singularities. And the point is, we need F to be analytic in and on all of this entire contour. That's all we need. Okay. So, yeah, so here we go. So F integral F of C dz around C0. You'll notice this is an oriented contour, and these 3 are clockwise. So this is equal to 0. Okay. Now we can say this C0 contour, C0, C1, C2 plus C3, but since these are the opposite direction, they have a minus sign in them that comes out if I go integral f of z dz minus C1 dz plus f of z dz minus C2 This is the orientation. Okay. This is positive orientation. These were clockwise in here, therefore they're proper orientation now, not clockwise. Clockwise orientation.
Question.
Yeah.
What did C naught equals C1 plus C2 plus C3?
No, C naught, this is the entire integral.
Okay.
Okay. So it's, it includes going all around the outside plus these 3. These are clockwise, of course these 2 cancel. So what's going to happen though, and again, we're looking to the future, we're gonna have often a contour that vanishes at infinity, and we'll be able to replace it just by little contours around these singularities. So yeah, there are a lot of proof by sketch and circle in this field. So yeah, you've got singularities here, you just go around them by this construction. And by going around them by this construction, you still have Cauchy's integral theorem. Okay. And then you've got the outside contour, C0, equal to the 3 properly oriented inside contours. Okay. Good. So we'll end this with the all-time basic integral here. It says home, we're carrying my this application here reminds us of our Fourier series work. We'll do this one once and for all, and almost everything follows from it. So an important example. We're looking at the integral, closed integral dz z to the nth power around c sub r, where c sub r equals a circle of radius r, circle of radius r. And it's going to be properly, positively oriented. So this is essentially what we just did a few minutes ago. Okay, circle of radius r, already drawn. So we're in C here. Circle of radius r around the origin. So this is the, and we'll draw the orientation as well. So this is the one where we can do z r e to the I theta dz I r e to the I theta e theta. And now we'll go to our integral here. It looks like it's going to be 0 to 2 pi. This time we're going around the entire circle. I r e to the I theta e theta. Z to the n r to the n e to the I times n times theta. So we can simplify this. We have 1 over r to the n minus 1 integral 0 to 2 pi e to the I n minus 1 minus n theta theta. So what do we get here? N equals 1. Oh, I left the I out, didn't I? Don't lose the I there. So if N equals 1, so if N equals 1, we have I 1, 1. So this is simply equal to 2 pi I. N equals 1. And for all others, it's just going to vanish. We're going to closed integral with an antiderivative. 0 and not equal to 1. Yep, and this is the all-time integral here. What do you think would happen if you went around this circle twice? Integrate from 0 to 4 pi.
You still get 0. Or
You'd either get 0 or 2 pi I times 2. Right? So every time you go around the circle, you just pick up another 2 pi I. We're generally going to go around once, but you see the idea there. At the point where you have the parametrization, the parametrization can go around this as many times as you want, and you would just keep picking up another 2 pi I every time you went around. Okay, good. We'll start with this next time. It's a great example, and it's just as fundamental to this subject as the analogous thing was for Fourier series. Good. I didn't write your homework down, did I? I'll make it up to you next time.
We rejoice.